Somebody told me this morning that human beings will never travel to another star. Just like that. Flatly. And I wanted to ask him, really? You've done the math on that? Because I have. And the answer is not what you think it is. Not even close. Let me ask you something first. Something simple. How far can you walk in a day? 10 miles? 20, if you're really motivated. Okay? Now, how far could a human being walk in an entire lifetime? Let's say 70 years of walking every single day. You do the rough arithmetic and you get something like 250,000 miles, which sounds enormous, which sounds like more than a person could possibly need. But here's the thing. The moon is about 250,000 miles away, so an entire lifetime of walking every step of every day just barely gets you to the moon. And the moon is, cosmically speaking, right next door. It's so close that when you look at it on a clear night, you are almost touching it. You can see craters with your naked eye. The moon is our neighbor's front porch, and a lifetime of walking gets you there. That's where we are, physically, as biological creatures on this planet. Now, the nearest star to our sun, Alpha Centauri, a lovely little system, actually 2 stars that orbit each other, plus a red dwarf companion called Proxima, that's about 4.2 light years away. Light years is one of those phrases people toss around without really feeling what it means, so let me make it very physical for you. Light travels at 186,000 miles per second, not per hour. Per second. In 1 second, light goes around the Earth 7.5 times. And a light year is how far light travels in an entire year of doing that. 4.2 light years to the nearest star, that's about 25 trillion miles. If we tried to walk to Alpha Centauri at our comfortable human walking pace, and I know we can't, the vacuum of space tends to be inhospitable, it would take us roughly 900 million years. The Earth itself is only 4.5 billion years old. We are talking about 1/5 of the entire age of the planet just to walk next door in cosmic terms. And I want you to sit with that for a moment, because that's the real size of the universe trying to announce itself to your nervous system. So, you are sitting there thinking, this is hopeless. This is a tragedy. We're stuck here. Our little candle of a civilization is going to burn out right here in this solar system and never see anything else, and the entire galaxy is just going to ignore us and go on without us. I can see it on your faces. The universe has made you feel very small and you don't like it. But here's where it gets interesting. Here's where the physicist gets to come in and say, oh, wait. You're thinking about this wrong. You're making an assumption that almost everyone makes, and it's completely understandable, and it is also completely incorrect. The assumption is this, that when we talk about how far humans could travel in a lifetime, we are bound by the outside observer's sense of time. We are not. Let me explain what I mean. And to do it, I need to tell you about a man named Hermann Minkowski, who was, and this is a wonderful historical irony, one of Albert Einstein's math teachers. Einstein, when he was a student, was not particularly impressive in Minkowski's class. Minkowski reportedly thought Einstein was a bit of a lazy dog. And then Einstein publishes the special theory of relativity in 1905, and Minkowski looks at it, and rather than being embarrassed, he does something marvelous. He takes Einstein's ideas and he reformulates them in a geometric language that even Einstein initially thought was overly complicated. Einstein came around eventually, because what Minkowski revealed is that space and time are not two separate things. They are one thing, space-time, and the universe is geometrically structured in a way that produces the most astonishing consequences for travelers. Here is one of those consequences. When you move very fast, really fast, close to the speed of light, time literally slows down for you relative to everyone who is not moving with you. This is not a philosophical metaphor. It is not a trick of perception or measurement. It is a real physical geometrical fact about the structure of the universe, and it has been verified experimentally precisely many times over. We put atomic clocks on airplanes, ordinary commercial airplanes, and we fly them around the world, and when they come back, they are measurably actually behind the clocks that stayed on the ground. The effect is tiny because airplanes are slow, but it's real. It's exactly the amount Einstein's equations predict. The universe is genuinely, structurally built this way. Now, the effect gets enormous when you approach the speed of light, and here's where I want to do a proper thought experiment with you. Not a hand-wavy analogy, but the real thing. Imagine a spacecraft, nothing magical. Just a spacecraft with a good engine, an engine that can produce a constant acceleration of 1g. 1g meaning the passengers feel a force exactly like the gravity you feel sitting in your chair right now. This is actually a beautiful choice of acceleration for reasons that will become clear in a moment, but the physics of it is what I want you to see. If you have a spacecraft that can maintain a constant 1g acceleration, you don't need artificial gravity because the acceleration itself pushes you into your seat with the same comfortable weight you feel on Earth. You wake up every morning in the spacecraft and everything feels normal. Now, what happens to such a spacecraft over time? For the first year or so, you are just accelerating. Classical mechanics, nothing too exotic. After about a year of 1g acceleration, you're going fast enough that relativistic effects start becoming significant. You cannot actually reach the speed of light. The math absolutely forbids it for reasons I'll get to, but you can get extraordinarily close to it. And as you do, something remarkable happens to time as experienced on the spacecraft. The time on board, the proper time physicists call it, begins to diverge radically from the time ticking away back on Earth. The equations were worked out carefully by a physicist named John Scott Russell. No, wait, I'm getting confused. The relativistic rocket equations were formalized properly in the 1950s by people like Herbert Dingle and Eugen Sanger working off Einstein's foundations. And what those equations tell you is something that should make you gasp. Let me tell you the actual numbers. A spacecraft with constant 1g acceleration, spending half the trip accelerating and half decelerating so it actually arrives somewhere rather than shooting past it, such a spacecraft could reach Alpha Centauri in about 3.6 years of ship time. Not Earth time, ship time. From the astronaut's perspective, the wristwatch on their arm, the beating of their heart, 3.6 years. Meanwhile, back on Earth, about 6 years have passed. Already the divergence is beginning. Now let's go farther. The center of our galaxy, the Milky Way, is about 27,000 light-years from Earth. In Earth time, an astronaut traveling to the galactic center at 1g acceleration would take about 27,000 years to get there. The entire human civilization, from the invention of writing to right now, has unfolded in about 5,000 years. So forget it, right? Hopeless. 21 years on the spacecraft. 21 years of ship time. The astronaut, by the time they reach the center of the Milky Way, is 21 years older than when they left. They could leave Earth in their 20s and arrive at the center of our entire galaxy, 100 billion stars, the great black hole Sagittarius A, the dense glittering core of everything we're part of. They could arrive there in their 40s. In a single human lifetime. I want you to really let that sink in, because I think it hasn't sunk in. I am telling you that the geometry of the universe allows a person, in principle, to travel to the center of their home galaxy in a single human lifetime. The universe is not as locked to us as it appears. The bars of the cell are not as thick as they look. There is a door, and the key is relativity. But don't go booking tickets yet, because now I have to tell you about the engineering, and the engineering is where the dream meets the wall, and the wall is very hard. The problem is energy. It is always energy in the end. One of the things I have found after a lifetime of doing physics is that the universe is perfectly happy to tell you the rules. It's quite generous that way, but it is extraordinarily, almost sadistically, demanding about the price of doing anything interesting with those rules. To accelerate a spacecraft to a significant fraction of the speed of light, you need an absurd amount of energy. Let me give you the flavor of just how absurd. Suppose you want to send a spacecraft carrying one person. Let's say the spacecraft, with all its fuel, weighs about 1,000 tons at launch, which is not outrageous for a serious deep space mission. Actually, it's modest. The Saturn V rocket that took people to the moon weighed about 3,000 tons. So we're talking about a relatively small, efficient vehicle. What fraction of the speed of light do you need to reach for the relativistic time dilation to become useful? Let's say you want to reach 90% of the speed of light. The energy required, just for the acceleration phase, is roughly comparable to the entire energy output of the sun over several months. The entire sun. Every second, the sun releases about 3.8 times 10 to the 26th watts of energy. We would need something comparable to hundreds of days of that, all focused into propelling our small spacecraft. The Earth's total electricity consumption in a year is a laughably tiny fraction of this. We are talking about energy scales that are, with our current technology, simply incomprehensible. Now, the most optimistic proposals, and there are real serious physicists who have worked on these, involve things like antimatter rockets, where you combine matter and antimatter in perfect annihilation to get the maximum possible energy out of mass. The equation E equals mc squared tells you that a kilogram of matter perfectly converted to energy releases about 90 petajoules, 9 times 10 to the 16th joules. The entire Hiroshima bomb released about 6 times 10 to the 13th joules. So 1 kilogram of perfect matter to energy conversion is about 1,500 Hiroshima bombs. That sounds like a lot. The trouble is, to get a 1,000-ton spacecraft to 90% of the speed of light with perfect antimatter annihilation, you'd need the equivalent of millions of tons of antimatter. We currently produce antimatter in quantities of nanograms per year at particle accelerators at an energy cost that is unimaginably greater than the energy stored in the antimatter itself. We make it. We can make it. But the scale required is so far beyond what we currently produce that it's like saying a person can run a marathon because they've successfully stood up from a chair. Then there's the proposal by an astronomer named Freeman Dyson, a remarkable man, one of the clearest thinkers I've ever encountered, who in the 1960s seriously worked out a design for a spacecraft called Orion, which would be propelled by detonating nuclear bombs behind it. Hundreds of nuclear explosions, each one pushing the ship forward. It sounds insane. It is in a sense insane. But the physics was completely sound. The engineering was challenging, but not obviously impossible. And the velocities achievable with fission bombs alone were modest, a few percent of the speed of light, but with fusion bombs perhaps 5 or 10%, which would actually get you to Alpha Centauri in a few decades of ship time. Dyson said in his characteristically direct way that if you're going to do interstellar travel seriously, you have to be serious about the energy. Project Orion was real. It was funded by the United States government. They tested hardware. They flew small-scale models. And then the Partial Nuclear Test Ban Treaty of 1963 made it effectively illegal because the concept requires detonating nuclear devices in space, and the treaty wisely prohibited exactly that, for reasons that had nothing to do with interstellar travel and everything to do with not blowing up the world. Dyson was heartbroken. He has said that Orion was the most practical interstellar spacecraft concept ever seriously studied, and that we killed it for political reasons that made sense but still broke his heart. Don't shake your head. I know what you're thinking. You're thinking this all sounds fantastical. You're thinking I've been telling you all these marvelous numbers, but none of them connect to anything you could actually build in a garage or a factory or even with all the resources of a civilization. And you're right that there's a gap, a large gap, between what the physics allows and what the engineering can deliver. But I want to push back on the idea that this gap is infinite or even fixed, because there's something important about the history of impossible things. In 1900, Lord Kelvin, one of the most accomplished physicists who ever lived, the man who defined the absolute temperature scale, knighted by Queen Victoria, showered with honors, Lord Kelvin said publicly and confidently that heavier-than-air flight was impossible. He was not a foolish man. He was not ignorant. He simply failed to anticipate a solution space he couldn't see from where he was standing. 3 years later, Orville Wright was airborne at Kitty Hawk. In the 1930s and 40s, most serious scientists believed that nuclear energy was a theoretical curiosity with no practical application. By 1945, it had reshaped the entire planet. By 1954, the first nuclear power plant was generating electricity. I am not saying that antimatter drives or fusion rockets are right around the corner. I am saying that the certainty with which people declare things impossible has a very poor track record compared to the actual behavior of human ingenuity operating over centuries. The physics permits interstellar travel in a human lifetime. The engineering doesn't yet. That gap is real, but calling the gap permanent is an assumption, not a calculation. Now let me tell you something even more surprising, because I've been holding it back and I can't hold it any longer. Something that goes even beyond what I've already told you. Something that, and I say this as someone who has spent his whole life trying not to be mystified, still strikes me as the most peculiar thing about the universe's relationship with speed and time. There is, in principle, no speed below the speed of light at which you cannot travel a theoretically unlimited distance in a finite amount of ship time if you are willing to accelerate long enough. Let me repeat that. There is, in principle, no destination in the observable universe that is unreachable in a single human lifetime, given sufficient energy and sufficient acceleration. The Andromeda Galaxy, our nearest large galactic neighbor, 2.5 million light-years away, would take about 28 years of ship time under constant 1g acceleration. You could leave Earth as a young adult and arrive at Andromeda in your late 40s. Meanwhile, 2.5 million years would have elapsed on Earth. Everyone you knew would be incomprehensibly ancient history. Every structure, every language, every nation, every idea of your civilization would be as remote to the people on Earth as the tool-making of Homo habilis is to us. But you, the traveler, would be 28 years older. You would arrive, and you would look out the window, and you would see the great disk of Andromeda spread before you. And if you had enough energy, enough fuel, or whatever we eventually figure out about how to get energy from the vacuum or the stars along the way, the numbers keep going. 10 billion light years, the edge of the observable universe, still reachable in about 45 years of ship time. 45 years. From a baseline of nothing but the physics of Einstein's equations, this universe allows a human being to travel to the edge of everything we can see in less time than it takes for a child to grow up and become a middle-aged person. And now we get to something genuinely strange, genuinely unsolved, and I want to be honest with you about this because science requires honesty about its own limits. But there is a catch that is not about engineering. There is a catch that is about the universe itself. The universe is expanding. It's been expanding ever since the Big Bang. And not only is it expanding, it's accelerating in its expansion. We call it dark energy, which is a name that means roughly we have absolutely no idea what this is. Something is pushing space itself apart at an accelerating rate. The farthest galaxies we can see are receding from us at speeds that are, when you factor in the expansion of space between us, effectively greater than the speed of light. Not because they're moving through space faster than light, nothing does that, but because the space between us and them is growing. It's a different kind of faster than light, and it has a profound consequence. The observable universe is the sphere of everything we can in principle detect, about 46 billion light years in radius, is not the same as the reachable universe. Even with relativistic time dilation, even with infinite energy, there are galaxies that we can see right now but will never ever be able to reach because the space between us and them is growing faster than we could ever traverse it. The universe has a cosmic horizon, and beyond that horizon everything is receding faster than any traveler could follow. And we don't know exactly where that horizon is. We don't fully understand dark energy. We don't know if it's a cosmological constant, Einstein's old fudge factor, which he introduced and then called his greatest blunder, and which turns out to actually describe the data quite well, or whether it's some dynamic field that changes over time. We don't know if the expansion rate will increase, decrease, or stay the same. The answer to how far can humans travel in a lifetime genuinely depends in a non-trivial way on the answer to what is dark energy, and we don't have that answer. Anyone who tells you they do is selling something. I find this deeply exciting, not distressing. Exciting. The fact that the question, how far can a human go in a lifetime, connects all the way up to the deepest unsolved mystery in cosmology, this tells you something about what kind of universe we're in. We're in a universe where one simple, practical-sounding question pulls on a thread that leads to the very architecture of space and time and energy. That's a spectacular universe to live in. And let me make a connection that I think is important, because the physics is beautiful, but the physics in isolation is just a technical achievement. The physics matters because of what it means for us, for this remarkable species that has been here for, cosmically speaking, the tiniest sliver of time, and has already figured out enough about the universe to understand its own possible futures. Think about what it took for humanity to arrive at the knowledge I've been describing tonight. Thousands of years of people looking up at the sky and wondering. Aristarchus of Samos figuring out in 250 BC that the sun is far larger than the earth and the earth goes around it, and being mostly ignored for nearly 1/800 years. Copernicus, Kepler, Galileo rebuilding the picture of the solar system through genius and stubbornness. Newton synthesizing all of it into a mathematics of motion that lasted more than 200 years. Einstein arriving at the age of 26 with his miracle year papers, demolishing the foundations and replacing them with something so strange that even he wasn't sure what he'd created. All of this curiosity, all of this work, all of these arguments and experiments and calculations have led us to the point where we can actually calculate how far a human being could travel in a lifetime. Not guess. Calculate, that is not nothing. That is, in fact, one of the most extraordinary things I can think of that has ever happened on this planet. A species of medium-sized primates living on a rock orbiting a fairly ordinary star in the unfashionable outer arm of a spiral galaxy has figured out using paper and pencil and a great deal of stubbornness the geometry of space-time and the rules governing motion through the entire cosmos. We can sit here in this room and calculate the trip time from Earth to Andromeda. We have never been to Andromeda. Nobody has ever taken that trip. And yet we know the answer because we understand the rules. You might ask, and you should ask, it's a good question, whether any of this is ever going to be practical. Whether the engineering will ever catch up to the physics, and I genuinely don't know. I want to be clear about that. I suspect that something surprising will happen, that there's an energy source or a propulsion concept that we haven't thought of yet, or that we're thinking about in a naive early form right now the way Kelvin was thinking about flight in 1900. I think the history of science gives us every reason to be humble about declaring what future human beings will and won't be able to do with several more centuries of physics and engineering behind them. There's a wonderful concept that some physicists and engineers have explored, a laser sail or light sail, where instead of carrying fuel, the spacecraft is pushed by a beam of light from a powerful laser array back in the home system. The Breakthrough Starshot initiative, announced in 2016 by Stephen Hawking and Yuri Milner, proposed exactly this for sending tiny probes, not people, to Alpha Centauri at about 20% of the speed of light. No fuel on board, just a solar sail being pushed by an extraordinarily powerful laser. At 20% of the speed of light, Proxima Centauri is reachable in about 20 years, and with relativistic effects the ship time is very close to that, since 20% of light speed doesn't produce dramatic time dilation. The probes would be tiny, grams in mass, not humans. But the principle is real and it's been seriously studied. For human-scale missions, the energy requirements are so much larger that it almost seems like a different problem. But scale is not the same as impossibility. When you look at what our civilization consumes today versus what we consumed a century ago, the energy scales are completely different. Extrapolate forward, not a century, but 5 centuries, 1,000 years. What kind of energy infrastructure does a civilization have when it has had access to fusion power or Dyson swarms or technologies we can't yet name for centuries? The question isn't quite as closed as it looks, but here's what I really want to leave you with. Here's the thing I've been building toward this whole time. We tend to think of the question, how far can humans travel in a lifetime, as a question about limitation. It feels like a question about a wall. How tall is the wall? How close can we get to it? And everything I've told you tonight, the time dilation, the enormous energy requirements, the expanding universe, the cosmic horizon, all of it does describe constraints. Real ones. The speed of light is a real wall. Energy is a real constraint. The accelerating expansion of the universe imposes a real and permanent limit on the reachable cosmos. But look at what's inside that wall. Inside that wall is the center of the Milky Way in 21 years. The Andromeda Galaxy in 28. 50 years of ship time could carry a human being to parts of the universe that no light from our sun has yet reached. Inside the constraints is still essentially the entire observable universe, accessible in principle to a single human lifetime. And there is something about that, something about the specific geometry of Einstein's universe that I do not think is an accident. I'm not a mystic, and I'm not going to make claims about cosmic intention. But it is genuinely curious that the same equations that tell you you cannot exceed the speed of light also tell you that you can get as close to it as you want, and that getting close to it means that any destination, however remote, becomes accessible if you have the energy and the will. The universe closes one door, you cannot go faster than light, and quietly leaves another door open. But you don't need to, because close to light speed, any finite distance collapses into a manageable trip. I've spent my whole career trying to figure out what the universe is actually like, as opposed to what it seems like from where we're standing. And one of the things I've learned, one of the things the physics keeps showing me over and over, is that nature is peculiar in its generosities. It gives you something marvelous exactly where you expect to find only a brick wall. You find that you cannot break the speed of light, and you're disappointed, and then you realize that you don't need to. You find that the universe is larger than you can fathom, and you're overwhelmed, and then you realize that its very largeness is what makes it traversable, because in a relativistic universe, larger distances at higher speeds means more time dilation, which means the trip gets shorter in ship time, even as it grows longer in light years. The universe seems, to a physicist who's been watching carefully, almost designed to be interesting without being quite reachable. It is just large enough and just curved in its time the way it is that you can look out at all of it, calculate the trips, feel the possibility, and still have the work of centuries ahead of you before you can actually go. It's as if nature wanted to make sure we'd stay curious for a long, long time. And maybe that's the real answer to the question I started with. How far can a human travel through space in a lifetime? Further than you think, dramatically, almost absurdly further than your intuition says. The center of the galaxy, the neighboring galaxy, the edge of the observable universe in principle. All of it is there, written out precisely in the equations, available to any civilization that has enough energy and enough time to build the machines to make the journey. But when you look at where we are right now, the infant civilization, still burning fossil fuels, still arguing about basic things, still occasionally doing beautifully stupid things to ourselves, and you look at where we'd need to be to take that trip, you see that the real journey isn't the one through space. The real journey is the one through time. The journey from here, from now, from this room, to being the kind of civilization that could actually go. And that journey doesn't require any technology we don't already have. It just requires the one thing humans have always been surprisingly good at, even when we're being bad at everything else, deciding to find out.